In this video, we're going to look at refraction, which is the bending that a wave does when it moves from one speed to another. When I was a kid, we used to have to mow the lawn with this thing called a push mower. It was a nightmare, actually, but luckily at one point we got a better one. Beside the point, one of the things about a push mower is that thing, sometimes you'd have to go from the sidewalk to the grass and the sidewalk. And one thing you'd notice, if you were going at an angle and you hit the grass, it would kind of jerk the mower off into a new direction, okay? Because this wheel would hit the barrier first, this wheel would slow down and pull it a little bit to your right, and then you'd head up on the grass moving slower once the other wheel hit there. What we're looking at here is a real similar situation to the lawnmower. You have wave fronts approaching the boundary between the two mediums, and you see there's a change in direction. Okay, so what's happening is as this wave front hits, you can see the whole thing doesn't hit at the same time. This portion of the wave front hits first. It slows down first. And the slowing of the, for lack of a better term, the left portion, from my point of view, first causes it to bend in that direction, just like the lawnmower. And this is a consequence of going from fast to slow. Refraction doesn't just happen for light waves, it happens for all waves. This is a picture of water waves. It's kind of hard to tell, but they're moving along and reaching a barrier and bending. Now the barrier is actually a place where the water changes depth. That's what causes a change in speed of water waves. Over here is kind of a easier to see rendering of this. The light blue lines here are the wave fronts, and these orange lines are the rays that we draw perpendicular there. And you can see that as we move into the slower medium, it bends again towards this normal line. Sound waves can refract as well as light waves and water waves, and here's an example. You've got a warm layer of air near the ground and a cool layer of air up high. The sound actually travels faster in the warm air, you should recall from before, and this boundary that we're talking about is kind of a gradual boundary. So what happens is the sound that's created here does bend away, but it's a more gradual thing. It doesn't just hit a solid boundary and suddenly shift. It's a gradual shift away. So this guy's blowing his trumpet and the dog's able to sleep because the sound's being carried up and away. Now if the situation were reversed and you had the warm air on top and the cool air below, the sound would bend the other way and it would carry very well. A lot of cool things happen when light refracts. You get some consequences like swimming pools appearing shallower than they really are. A pencil in a glass of water looks bent, and stars twinkle. Okay, all this stuff is happening because the directions of the light rays change, and this is all because of refraction. I'm sure you thought when your mom was singing Twinkle, Twinkle, Little Star to you, she was just trying to entertain you, but it turns out she was teaching you physics. Looking at the refraction of light again, when you change speeds going from one medium to another, you're going to get this refraction. You also notice you get a little reflection off the surface. You get a little bit of both. Now this refraction, here we're going from air to water. So we're going from a fast medium to a slow medium. And I want you to see how this angle here gets a little smaller as that happens. Okay, we can actually pull out this little protractor here and we can see that's true. And we're going at about 45 degrees, and here we're at about 32 degrees, so we do bend in. The slower you go, in other words, when you go into materials that have even slower speeds of light, you actually bend a little more. When I change this to glass, you can see that the angle decreased even further. Now this goes both ways. If I had light coming up out of the material and going into the air, the angle would actually grow. I would go from the smaller angle to a bigger angle, so it goes both ways. What I'd like to do now is look and see how this notion of apparent depth works. So here we've got a mirror at the bottom of a dish of water, and we're shining light in here. And you can see the refraction that's happening. The light bends a little towards the normal as it goes in, it comes down, reflects, and this time bends away from the normal. Now, our eye, when we look down here and look in, we are not going to see the mirror down here at the bottom. We're going to see it shallower. And the reason is our eye has a really difficult time imagining bending light. And so what we always do is we see images where the outgoing and incoming rays seem to converge. So if you draw lines here of these outgoing rays, they seem to converge somewhere around in this neighborhood, okay? That really means that we would see the mirror as this deep instead, okay? And this is true for anything in water. It always looks shallower. It could be a fish, it could be a rock, it could be a scuba diver. It's not going to look as deep as it actually is. Here's another example. You've got a fish down here a couple meters below the water, and this guy's looking and he sees a fish over here. Okay, again, this is the same idea. The light coming from the fish's eye is coming up, refracting when it reaches the surface. And if you trace that refracted ray back straight, you'll see where he sees the fish's eye. Okay, imagine if he was trying to spearfish. This would be pretty brutal. He would aim up here, no fish there, he goes home hungry. All right, this is cool. Look at this very full-looking mug of root beer. When we place it in water, we can actually see how unfull it is. The glass has plenty of thickness, right? It would have to. And it just doesn't look so full. Now, the question is, how come it looks like the liquid goes from edge to edge? The answer, of course, is refraction. If you watch these light rays that are coming from the liquid, when they hit the surface, they refract off the surface and come to your eye. And of course, again, we see them from coming straight back and we get our full mug. Very cool. Very tricky. The atmosphere can cause refraction too. Even though the speed of light in air is very close to the speed of light in a vacuum, when the air is heated or cooled, it actually changes speed a little bit. And here is a cool example known as a mirage. When you have hot air really close to the ground, it can cause a layer of air in which the speed of light speeds up. And if it's hot enough, it can speed up quite a bit. That's sometimes why you see heat waves coming off of a hot surface. You can see that in this picture, but what you can also see is what looks like water on the ground. You see the cars reflected in the apparent water, and that's actually a mirage. This is not really water on the ground. So what's going on? We'll use this diagram to illustrate. Here's a tree sending off a light wave, and this light wave would normally come and hit the ground, right? But this hot layer of air near the surface here is causing the light to refract, and it refracts so much that it actually comes back up. What's happening is, once again, our brain is being fooled by bending light. This light is entering the eye at this angle, so naturally a line that goes straight back from there to where the tree is on the ground. Okay, we'd literally see that out here, by the way, not all the way back here. That's our mirage. Now you think, well, what's that got to do with water? What that has to do with water is our brain thinking, hey, if I'm seeing a reflection on the ground, that usually means water. It could be a puddle, it could be a lake, it could be anything, but that's when I see reflections on the ground. And so our brain thinks it's water. Silly, silly brain. So easily fooled. All right, we have one last application of refraction before we go. The sun, as it starts to set, sends light through this very long stretch of atmosphere, which has quite a bit of changing temperature, and it refracts the light downward. And once again, seeing this light straight back from the last direction it was traveling, we see the sun up here. Now the sun's actually gone down below the horizon, but we still see it. This actually increases the length of our day by about 5 minutes. Isn't that cool? Thanks for stopping by.